Hello, welcome to the short presentation of SyncTwin, treatment effect estimation with longitudinal EHR data. I'm the presenter, Zhaozhi Qian. In this presentation, I will introduce and formulate the problem of estimating the causal individual treatment effect in the longitudinal setting from observational data such as EHR. In this problem setting, we consider the longitudinal outcome with point treatment as illustrated in the figure on the right. Here, for all the individuals in the data set, we observe the treatment allocation at a given point in time. And the treatment allocation will divide the timeline into the pre-treatment period and the post-treatment period. And the post-treatment period is illustrated by the gray area in this figure. We observe the outcomes both before and after treatment. And we also observe the temporal covariance that leads to the treatment decision. Just as all the observational studies, the treatment allocation is subject to the confounding bias, and we will use those temporal covariance to adjust for the confounding bias. A requirement for such an estimation method is that the method should be interpretable and trustworthy. We'll expand on those notions in a short time. The longitudinal treatment effect estimation is very significant and has many clinical applications. As we all know, many clinical trials are underrepresentative for the general population because of the small sample size and eligibility criteria. Moreover, the real-world electronic health records data contains a lot more samples, which makes subgroup identification and measuring the heterogeneity within subgroups possible. And this can lead to personalized treatment decision and precision medicine. Last but not least, the observational data set contains longer outcomes, both positive ones and adverse ones. However, the clinical trials are often done in a shorter time span and is inadequate to fully measure the long-term outcomes. Before diving into the method, I wish to explain the notion of explainability and trustworthiness. There are different notions of interpretability. Here we adopt the notion of interpretable by examples. This means that for the estimation of any target individual should be explainable by a small set of contributors. And the algorithm can also measure the weight, measure the contribution of each contributor. Here as an illustration, we look at the figure on the right. We want to estimate for one target individual, what can we do to explain the estimation? Well, we can explain it by finding a few contributors that are really similar to the target individual, and that drives the algorithm's decision. And in fact, we can present those contributors and their contribution to the clinician, and the clinicians can then validate whether those contributors are really close to the target individual by their domain knowledge. In terms of trustworthiness, this property is also highly desirable, especially when we use the algorithm to make personalized treatment decisions. For that application, we need to identify the individuals whose ITE cannot be reliably estimated, which is unfortunately always possible because the presence of outliers. A trustworthy method should warn the clinician not to trust the estimate and fall back to their domain knowledge and use their judgment. Now, the SyncTwin method includes 3 steps: encode, synthesize, and estimate. For any target individual, we find very few contributors from the opposite treatment group. The first encoding step will use the temporal covariance will encode the temporal covariance into fixed representation vectors using deep neural network. In the second step, we'll build certain contribution weights based on the representation vectors, and those weights are clearly measuring the contribution of the contributors and therefore making the method more interpretable. Based on the same set of weights, the algorithm estimates the counterfactual outcomes by performing the weighted average on the selected contributors. And such counterfactual outcome can be computed both before and after treatment, and we can use the difference between the estimated and the real outcome before treatment to measure the trustworthiness. We performed extensive simulation study to illustrate that the synthetic twin consistently outperformed the baselines on a variety of scenarios. We also bring the method to the real data and attempt to replicate a clinical trial with observational data. And here we took a large-scale clinical trial called heart protection study, which enrolled more than 10,000 patients and lasted for more than 1 year. And we used electronic health data set called CPRD in the UK, which roughly covers 10% of the UK population. And after applying SyncTwin on the CPRD dataset, we managed to replicate the finding of the clinical trial. This gives us evidence that SyncTwin is applicable in many real-world complex datasets. If you're interested in knowing more, please check out the longer tutorial and also visit our website. Thank you.